In previous videos, we talked about the rank and the nullity of a linear transformation. In this video, we'll prove a big theorem. We'll prove what's called the rank nullity theorem. It's going to link the size of the kernel with the size of the image. So let V be a finite dimensional vector space. W can be any vector space. Let T from V to W be any linear transformation. Then the nullity of T plus the rank of T is going to be equal to the dimension of V. All right, so this is what we want to prove in this video. It's going to take a bit of time. It's not an easy result, so don't worry too much if I keep going. It was meant to be that way. All right, so what we'll start with a basis for the kernel. So let B, which is V1, let me put a kernel here, otherwise we'll get confused. Kernel of T, which is V1, V2, Vk, be a basis for the kernel of T. So the dimension of the kernel we're assuming is K, and that means the nullity of T is K. All right, now we have a linearly independent set in V. It's not a basis for V, it's a basis for a smaller subspace. And so what I'll do is I want to build it from this. I want to build a basis for the whole vector space. All right, so now I'm going to take B of V. So I'm going to start with the same elements that I had in the base for the kernel. And then I'm going to keep adding vectors until I get a basis for V. So let's this be a basis for V containing B of the kernel of T. In section 1.5, we learned how to do this, how to build up a basis from a linear independent set. That's what we're doing here. Notice that I have n elements in this, and so I'm assuming that the dimension of V is n. All right, so I claim that I can build a basis for the image, and that's going to be linked to the rank. I'm going to get a basis for the image of T by ignoring these and keeping those and applying T to them. So I'm going to apply T to K plus 1. I'm going to apply T to Vn. And I claim that this is a basis for the image. All right, so we'll conclude afterwards, but notice that this has n minus k elements, so n minus k for the rank, k for the nullity, and then the total is n. That works. All right, so that will prove it, but it's a bit stronger. We actually construct a basis, which is nice. All right, so I need to prove two things to prove this is a basis. I need to prove that it spans, so let's start with that. I need to prove that this spans the image of T. All right, so I'm going to take W in the image of T, and so that means W is T of V for some V in V. I have a basis for V right here, so that means I can write this small v as a linear combination of these. So since we could do it in a unique way, but that doesn't matter right here. So since BV is a basis for V, then V equals A1 V1 plus A2 V2 plus AK VK plus AK plus 1 VK plus 1 plus AN VN, right? Every time I'm amazed by how many terms I have to write. All right, so this is V. Let me move it a bit left so that it looks nicer. This is V, so I want W. I'm going to apply T to it. So W, which is T of V, equals T of A1 V1 plus AK VK plus AK plus 1 VK plus 1 plus AN VN. Since T is linear, I can split this. I can split it as A1 T of V1, AK T of VK, AK plus 1 T of VK plus 1, and then AN T of Vn. Now, V1, let's go look at these ones, where they came from. V1 through Vk was a basis for the kernel. That means if I apply T to them, I get 0. And so all of these, right here, this would give you 0. This, I meant for the whole thing. This gives you 0. And so the whole start of this disappears, and I end up needing only the elements from Vk plus 1 to Vn. All right, so I started with a random element of the image, and I wrote it as a linear combination of my candidate for basis, and so that means that W is in the span of B image of T. And so the span of B image of T is the image of T. All right, that's part 1. We proved that this spans image of T. Now we want to prove it's linearly independent. All right, so I'm going to move to the next page. I want to prove, actually, let me start here so you can still see. B image of T is linearly independent. All right, so I'm going to start with a linear combination that gives me 0. So assume, let me just look back to remind you, these are the elements in the image. And so assume A1 TV1 plus AN T, oh, sorry, VK, so plus 1. I'm sorry, I started at the wrong level. So let's start again. VK plus 1 plus AN TVN. Let's assume that this gives us a 0 element in W. All right, we're going to do the opposite of what we've done over here. Here we split. Now we're going to put them back together. So that means, since T is linear, that I could write this as AK plus 1 VK plus 1 plus AN VN. All right, so now I have an element that if I apply T to it, I get 0. That means that that element of V, is in the kernel. But we have a basis for the kernel, that's V1 through Vk, and so we could write this linear combination as a linear combination of V1 Vk. All right, so maybe you see what's going on. I actually have a single linear combination here. If I send all of this to the other side, what I get is that minus A1 V1 plus minus AK Vk plus AK plus 1 Vk plus 1 plus AN Vn equals 0. We're in V now, so 0 V. I had a moment there where I wasn't sure where I was. All right, but since I have a basis for B, it is linearly independent. And so all of these coefficients must be 0. All right, so we don't care about these, but we care about those. Those were the coefficient that we started with in our linear combination. And so since AK plus 1 equals 0 and AN equals 0, we just proved that the image of the basis that we have for the image of T is linearly independent. Whew. All right, well, let's recap. I'm sure you lost track. All right, what did we do? We have, first of all, the basis for the kernel was V1 through Vk, and so that means that the nullity of T is the dimension of the kernel, so it's the number of elements there, so that's K. All right, the basis for V was V1 through Vn, and so that is a basis for B is a this is a basis for V, so the dimension of V is n. And the last thing we proved is that the basis for the image of T is Vk plus 1, T of Vk plus 1, T of Vn. And so the rank of T is equal to the dimension of the image. That's n minus k. All right, so that's what we have. And so as claimed, the nullity of T plus the rank of T, that's n minus k plus k, that's equal to n, which is the dimension of V. And we're done. All right, good. This is an important theorem. It was a nice proof. It's a bit of a long proof, but it's nice because we actually are building basis and we're using what we've proved before. We're using that we can build up a basis from a basis of a smaller subspace.